Welcome to This Explainer. We are jumping right in today to look at an absolute unsung hero of modern electronics. Every single time you play a digital audio file or take a reading from a smart sensor, basically anytime you use anything with a microchip, there's this silent little worker in there translating raw, messy electrical signals into perfectly usable data. I'm talking about the operational amplifier, or as we usually call it, the op-amp. It's a tiny component that literally performs magic with electricity. And by the end of this, you're going to see exactly how it shapes the entire digital world around us. Okay, let's dive into this. Here's our roadmap for today. First, we'll meet the operational amplifier. Then we'll check out its noise-canceling core, see how we tame it with negative feedback, compare the ideal versus practical realities, and finally, look at how it does actual math in the physical world. We're taking an analogy-filled journey today. We're skipping the dense textbook numerical problems, because let's be honest, we don't need them to understand the really fascinating concepts of how this all actually works.
All right, part one, meet the operational amplifier. I want you to imagine, just for a second, that you're a tiny, fragile electrical signal. Maybe you're the faint little pulse from a heartbeat monitor. You are about to enter a highly versatile electronic component that's going to give you the juice, the strength, to actually be read and understood by a computer.
And that component is the operational amplifier. You know, historically, long before computers relied purely on millions of lines of software code to do math, they used physical chips just like this to literally calculate voltage. The hardware itself was doing the math just by manipulating electrical currents. How cool is that? Now, what's really interesting about this slide is when you look at this physical integrated circuit, this little IC chip, it's just incredible to think that all the complex transistors and resistors needed to do that heavy lifting are packed onto this tiny, unassuming piece of silicon. It's wild that this microscopic piece of hardware accomplishes so much inside our devices, acting as a multi-stage amplifier to boost and process those signals. Moving on to part two, the noise-canceling core. So as our hero signal travels through wires to get to this chip, it immediately runs into a villain: interference. The physical world is noisy, right? It's completely filled with stray magnetic fields and radio waves that are just waiting to distort our signal. To defeat that villain, the op-amp uses a differential amplifier at its very core. Think of this exactly like a pair of high-end noise-canceling headphones. When you wear those on a flight, the headphones are actively listening for that low, droning hum of the airplane engines. We call that a common mode signal because it's hitting both the left and right inputs equally. The headphones reject that hum, but they perfectly amplify the music you actually want to hear, which is our differential mode signal. Well, the op-amp is doing exactly the same thing, just with electricity. And this brilliant little graphic illustrates the concept in action. Notice how that clean signal on the top left gets infected by a really messy low-frequency hum. But because that exact same hum enters both input 1 and input 2 equally, the differential amplifier acts just like those headphones. It recognizes the common mode noise and literally cancels it out. Bam, gone, leaving us with a perfectly clean output signal right there on the right. Okay, part three, taming with negative feedback. So we've got our clean signal and the op-amp is ready to boost it. But here's the catch. Without strict control, our signal's journey is going to crash spectacularly, which brings us to the whole concept of feedback. Imagine, if you will, getting into a sports car where the accelerator is just permanently stuck to the floor. The exact second you turn the key, you are rocketing at maximum speed with zero control. Well, an op-amp naturally has such insanely high voltage gain, we're talking often over 100,000 times, that if you just feed a raw signal into it, it instantly hits its maximum electrical limit. We call that state saturation, and in that state, it's basically useless as a precise tool. To fix this massive problem, engineers use something called negative feedback. Think of it like a driver making constant, tiny microcorrections to the steering wheel just to stay perfectly centered in a lane. Or, like a thermostat constantly checking a room's temperature to keep it exactly at 70 degrees. What we do is take a little bit of the op-amp's output and literally feed it back into the negative input. It acts as a set of brakes. It perfectly prevents the chip from driving into that heavy saturation zone. And as you can see here, this vital trade-off gives us total control. By sacrificing that raw, extreme voltage gain, we actually stabilize the input and output impedances. Even better, we significantly widen the bandwidth. That means the amplifier can handle a much, much wider range of frequencies with total accuracy. It's a fantastic trade-off. Section 4, ideal versus practical realities. Because, let's be real, while textbook theory is nice and neat, it almost never perfectly matches the messy, physical real world we actually live in. In a textbook, an ideal op-amp is kind of like one of those perfectly frictionless physics problems you did in high school. It supposedly has infinite voltage gain, it draws absolutely zero current from the input, and it pushes out a signal with zero resistance. Sounds great, right? But the practical op-amp, the one we actually have to build out of silicon, has physical limitations. It has very high but definitely limited gain, it has low but non-zero output impedance, and it does actually draw a microscopic amount of current.
And since manufacturing is never literally 100% flawless, the tiny transistors inside are never perfectly matched. This creates a sort of real-world friction that we call input offset voltage. Think of it like a bathroom scale that reads a few ounces even when nobody is standing on it. It just means that even if you feed absolutely zero signal into the chip, a tiny accidental voltage might still sneak out the other side. So engineers have to cleverly design their circuits to balance out these real-world imperfections and keep the signal pure.
All right, bringing it home with Section 5, Math in the Physical World. We have cleaned our signal, we've tamed the crazy power with feedback, and we've accounted for real-world friction. Now let's move on and see how this all builds to a thrilling climax, actually using this hardware to perform real mathematical operations. Take a look at this circuit right here. This is the summing amplifier. If you have ever seen a DJ or sound engineer working at one of those massive audio mixing boards, you have seen this exact concept in action. You've got a drum track on one channel, maybe vocals on another, a screaming guitar on a third. The summing amplifier literally takes the electrical voltage of all those separate individual inputs and it adds them together algebraically into one perfect combined master output.
But addition is really just the beginning of the story. If you look closely here, we have an integrator on the left and a differentiator on the right. And this is mind-blowing. By simply swapping the position of two incredibly basic components, a resistor and a capacitor, we completely change the advanced calculus operation that this circuit performs.
So the crucial point here is just how wonderfully intuitive this all is when we break it down using simple analogies. The integrator, that first one, acts exactly like a water bucket filling up. It accumulates the incoming signal over time, physically representing the area under a curve. If you feed it a steady signal, the output just ramps up steadily. The differentiator, on the other hand, that acts like your car's speedometer. It does not care how far you've traveled, it only reacts to sudden changes or the immediate rate of change. You don't need a massive whiteboard full of complex algebra to understand what the circuit is physically doing to the electricity.
It is literally hardware performing instant calculus. So the very next time you use a computer, or pull up a digital audio file, or rely on any piece of modern technology, take a second to think about what's really happening beneath the surface. It's not just software code floating in the ether. At its absolute core, it is tiny, beautifully designed chips like the op-amp physically wrangling the fundamental forces of electricity to do instant calculus and translate our messy world into the digital age. Which really makes you wonder, as our digital algorithms become infinitely more complex with things like artificial intelligence, will we soon be returning to specialized physical hardware chips to do the heavy mathematical lifting for us? Thanks so much for joining this explainer and keep exploring.